Act 1. The Challenge. The Surgical Theater. Mathematics Cambridge Exam Strategy. Welcome to the Surgical Theater, everyone. Today, we're basically putting on our scrubs, we're picking up our mathematical scalpels, and we are preparing to dissect one of the most notoriously intimidating topics in the entire Cambridge Additional Mathematics 0606 syllabus. I'm talking, of course, about kinematics, the study of motion. You know the drill: displacement, velocity, acceleration, and the absolute dreaded variable acceleration that literally forces us to abandon our basic formulas and step fully into the world of calculus. Look, if you're studying the 0606 or similar advanced syllabuses, you already know that mathematics at this elite level is not just about memorizing formulas. It's really about precision. It's about having incredibly steady hands under intense time pressure. It's about dissecting questions with surgical accuracy so you can extract every single available mark. So today, we're going to look at actual past paper questions, and we're going to analyze exactly how top-tier students build their flawless answers and, maybe more importantly, how average students completely throw away marks. Get your pens ready, clear off your workspace, take a deep breath, and let's enter the theater. Okay, let's dive into this by taking a look at the really big picture. I want you to imagine a spacecraft leaving Earth on a massive journey all the way out to Jupiter. Its initial direction is pointed straight at the gas giant. But will it travel in a perfect straight line? Well, if you think about the incredible, vast, multidimensional complexity of planetary orbits, the gravitational pulls of different moons, and moving through three-dimensional space, the answer is absolutely not. It's a chaotic curve. But hey, here's the incredibly good news for your exam strategy. We are not launching rockets to Jupiter today. For our Cambridge kinematics questions, we are exclusively dealing with particles moving in a single straight line. That's it. We are stripping away the totally chaotic three-dimensional aspects of the real world and focusing intensely on motion along one simple path. Now, this simplifies our mathematical universe tremendously, but, and this is a big but, it also means that the examiners expect absolute perfection in how you handle the tiny details along that one-dimensional line. There's nowhere to hide. I really love this quote from Maria Mitchell, the pioneering astronomer. She said, "Do not look at stars as bright spots only. Try to take in the vastness of the universe." Now, you might be wondering, what does astronomy have to do with kinematics? Well, I want you to apply this exact same mindset to your mathematics past papers. When you're sitting there and you look at an exam question, please do not just see isolated numbers or disconnected equations sort of floating randomly on a page. Don't look at them as random bright spots. You need to train yourself to see the vast, logical, beautifully interconnected system that sits right behind them. Every single velocity function you see is intimately connected to a displacement function. Every acceleration curve tells a specific, undeniable story about the object's speed. Once you understand the underlying system, the mechanics of how it all ties together, you completely stop guessing and you start operating with absolute certainty. So, here's our roadmap for today's session. First, the challenge, where we're going to diagnose exactly where marks get lost. Second, the vocabulary of motion. Third, we'll dive into the calculus engine. Fourth, we'll run a high-pressure interactive workshop. And finally, we'll wrap up with the final blueprint. Act 1. The challenge. The anatomy of a flawed answer. Let's look at two hypothetical students, Alex and Sam. Right, here is a classic challenge. This is pulled directly from the Cambridge June 2013 paper 12. It reads, a particle P moves in a straight line such that its velocity is given by v equals 36t minus 3t squared. The question commands you to find the distance of P from O when P is at instantaneous rest. Let's look at our first student type, who we'll call Alex the data dumper. Now, Alex actually knows a lot of mathematics, but under the ticking clock of the exam room, Alex panics. Alex just overloads the paper with raw facts, unlinked equations, and chaotic algebraic scribbles, essentially hoping and praying the examiner will somehow sift through the mess and find the right answer. There's no analysis there, it's just a brain dump. Total chaos. Then, on the flip side, we have Sam the sprinter. Sam works incredibly fast, feels super confident, brilliantly spots the trick to set velocity to 0, solves for time, gets an answer, gives a nice double underline, and races to the next question. Sam feels like an absolute genius, but guess what? Sam just lost 3 entire marks. Why? Because resolving this specific question requires way more than just knowing a bit of factoring algebra. Sam's failure is a strategic one, missing the actual command words of the question. To fix this kind of mistake, we're going to implement a strategic framework called PEAL. That stands for Point, Evidence, Explanation, Link. We'll be applying this directly to mathematics to literally force your brain to answer the right question. But obviously, before we can do that, we need to gather the right tools. Act 2. The strategy reveal. The vocabulary of motion. We have to clear the fog around our basic terminology first. Listen, you absolutely cannot build a solid mathematical argument if your fundamental vocabulary is mixed up. The examiners are fully aware of this, and they will deliberately use words that sound incredibly similar in everyday conversational English, but have vastly different mathematical implications. Now, what's really interesting about this slide is the final column in our table here. We all know the basic SI units, right? Meters, meters per second, but I really want you to look at the notation. Distance and displacement use the letters S, X, or Y. But velocity? Velocity isn't just represented by a letter V. Look closely. It is ds by dt. It is the exact rate of change of displacement with respect to time. And look down at acceleration. It is dv by dt, the rate of change of velocity with respect to time. This notation is secretly whispering the solution to you. That little d in ds by dt stands for a differential. The paper is explicitly telling you that the relationships between these variables are governed by calculus. It's practically screaming that to get from displacement to velocity, you must find the gradient of the curve. You must differentiate. So don't just look at this as a boring table of symbols. This is literally your instruction manual for the entire exam. But here is where we must make a truly vital distinction. And I mean it. This is the #1 trap that students fall into year after year. You must absolutely clearly differentiate between scalars and vectors. Distance and speed, those are scalars. They only have a magnitude, which just means a size. If you tell me your car is traveling at 50 kilometers per hour, that is a speed. It's a scalar. It doesn't tell me where you're going. But displacement and velocity, those are vectors. They have magnitude and a specific direction. If you tell me a car is traveling at 50 kilometers per hour north, boom, that is a velocity. In our straight line particle math that we talked about earlier, direction is incredibly simple. It's just positive or negative. Moving forward, positive. If my velocity is -5 meters per second, it simply means I am moving backwards or returning towards the origin. If you panic and treat a vector like a scalar in your exam, your positive and negative signs will be entirely wrong, and your final answer will completely shatter. Speaking of precise definitions, let's look at a phrase the Cambridge examiners are completely, unconditionally obsessed with. Instantaneously at rest. Picture a ball being thrown straight up into the air. It travels up, it reaches its absolute maximum height, it stops for a microscopic, invisible fraction of a second, and then it falls back down. That exact fleeting moment of stopping is when it is instantaneously at rest. I want you to treat this phrase as an absolute exam cheat code. The very second your eyes scan the phrase instantaneously at rest on an exam paper, your hand should automatically, without even thinking, write down v equals 0. That right there is your point in the Peel framework. You clearly state the mathematical truth, velocity equals 0. It is the immediate, non-negotiable first step you have to take to unlock the rest of the marks for the question.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Act 3, the transformation, the calculus engine. It's time to shift our focus to the mechanical core of kinematics.
Okay, you might remember from your earlier math studies those classic Suvat equations. You know, the formulas for constant acceleration. Those are wonderful, they really are. But here is the harsh, unavoidable reality for the 0606 syllabus. When acceleration is variable, meaning it actively changes over time, those constant acceleration Suvat formulas completely and utterly fail. If you look at an equation for velocity and it has a t in it, calculus is not just a fun option, it is strictly mandatory. You literally must use the engine. Think of calculus as a forward-moving pipeline. Step 1, you start with your equation for displacement, which we call S. Step 2, you want velocity? Okay, you differentiate displacement with respect to time. So v equals ds by dt. Step 3, you need acceleration? Easy. You take that brand new velocity equation you just made and you differentiate it again with respect to time. So a equals dv by dt. And this brilliantly illustrates a perfectly logical forward-moving process. Differentiation measures the rate of change, smoothly driving us from position down to speed and right down to acceleration. Let's actually dissect a real example together so you can see this in action. We are given the displacement s equals 5 plus 2t cubed minus 3t squared. Now Alex, our chaotic student from earlier, stares at this, gets overwhelmed, and freezes. But we are going to calmly apply the engine. We need velocity, so we differentiate. The constant 5, that just disappears into thin air. We pull down our powers, transforming the 2t cubed, bringing the 3 down to multiply by the 2 to make 6, and dropping the power, so that becomes 6t squared. Then the negative 3t squared smoothly transforms into minus 6t. Beautiful. Our velocity is 6t squared minus 6t. Now say we need acceleration. We just differentiate again.
That velocity equation drops down another level. The 2 comes down to multiply the 6, giving us a equals 12t minus 6. Now, what if the question asks when the particle is instantaneously at rest? Boom, we use our cheat code. We set that velocity equation to 0. So 6t squared minus 6t equals 0. We factor out the common term, which is 6t, giving us 6t times bracket t minus 1 bracket equals 0. And that quickly reveals that time t equals 0 or time t equals 1 second. Look at that. Clean, surgical, flawless calculus derivation. Absolutely no panic required. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, so to build a complete functional engine, we obviously need a reverse gear. If differentiation drives us forward down the pipeline, integration is the required tool we must use to reverse the entire process. Step 1. Let's say the examiner starts you off at the bottom with an equation for acceleration, a. Step 2. To move backwards up the pipe to velocity, you must integrate acceleration with respect to time, so v equals the integral of a dt. Step 3. To move backwards one more step to displacement, you integrate that velocity equation, so s equals the integral of v dt. And guys, this is absolutely crucial. When you integrate, you must never, ever forget your constant of integration, your plus c. Because without specific boundary conditions from the question to solve for that exact constant, your entire backwards journey is going to lead you to the completely wrong destination. I've seen so many A-stars vanish because of a forgotten plus c. Don't let it happen to you.
Act 4, the interactive workshop. Dissecting past papers under pressure. The clock is ticking down. Let's get right into it. Okay, challenge 1. You're going to have 60 seconds on the clock mentally for this. You open your paper and you are given the velocity function, v equals 15t minus 2t squared minus 25. The question, find the times when the object is instantaneously at rest. What is your immediate instinct here? What is the point in your Peel structure? Say it with me. Instantaneously at rest means v is equal to 0. So you immediately set that entire function equal to 0. Now you've got a quadratic equation. But it's kind of messy, right? It's got that negative leading coefficient. Let's make it super clean by multiplying everything by -1. That gives you a much nicer 2t squared minus 15t plus 25 is equal to 0. Now we factorize this clean quadratic equation, setting our two brackets to 0. When you do the math, you find your times are t equals 2.5 seconds and t equals 5 seconds. If you saw that pathway immediately in your head, congratulations, you are starting to think exactly like a Cambridge examiner. Challenge 2, we're going to find the flaw. Let's look back at our sprinter from earlier, Sam. Remember that June 2013 paper we looked at? The paper gave the velocity v equals 36t minus 3t squared. Sam rushed in, correctly set v to 0. Sam correctly factored it out, and perfectly found that the particle is at rest at time t equals 0 and time t equals 12 seconds. And then, Sam just stopped, drew a line under it, and moved on. What was Sam's fatal flaw here? Look at the command words. The question did not ask for the time of instantaneous rest. It specifically commanded you to find the distance when p is at instantaneous rest. Sam totally failed the link stage of our Peel framework. To actually fix this, we have to use our reverse engine. We must integrate the velocity equation to find the displacement, s. So integrating 36t minus 3t squared, add 1 to the power, divide by the new power, yields a displacement equation of 18t squared minus t cubed. Now we finally link it all together by taking that time we found, t equals 12, and substituting it into this brand new displacement equation. Let's do the actual substitution. When we substitute t equals 12 into 18t squared minus t cubed, we get 18 times 144, which is 2592, minus 12 cubed, which is 1728. Subtracting those two numbers gives us our final, brilliant, fully earned answer, 864 meters. If you mentally saw that you needed to integrate first and then substitute the time back in, you just rescued 3 massive marks that Sam carelessly threw away. Seriously, this is what surgical exam technique looks like. You don't just calculate blindly, you follow the chain of logic all the way to the very end, dictated strictly by the exact command words of the question. Let's tackle one more together. Challenge 3. This one is pulled from the November 2010 paper 13, question 10. We are given the displacement s equals the natural log of t squared plus 1. The command from the examiner is, find the distance traveled by the particle during the 3rd second. I want you to really think about how you would write a perfect Peel paragraph for this under pressure. The main point here is understanding what the phrase "during the third second" actually means in mathematical terms. It is a massive, massive trap. Alex, our data dumper, would probably just substitute t equals 3 into the equation and frantically write whatever decimal came out on the calculator. But that would be completely wrong. That approach would give you the total distance traveled over all 3 seconds combined, not just the distance covered during the third second specifically. So how do we correctly navigate this tricky time boundary?
So the crucial point lies right here in the examiner's commentary. You must internalize this logic. Think about a stopwatch. The first second is running from t equals 0 to t equals 1. The second second is running from t equals 1 to t equals 2. Therefore, the third second starts at exactly t equals 2 and finishes at exactly t equals 3. To find the specific distance traveled during that exact window, our strategy has to be to evaluate the displacement at t equals 3 and then subtract the displacement at t equals 2. Let's do it. At t equals 3, s is the natural log of 3 squared plus 1, which is 9 plus 1, so ln 10. At t equals 2, s is the natural log of 2 squared plus 1, which is 4 plus 1, so ln 5. Our final step is taking ln 10 and subtracting ln 5. And remember your laws of logarithms. When we subtract logs with the same base, we simply divide the arguments. 10 divided by 5 is exactly 2, so the exact, flawless final answer is ln 2. Mastering these highly specific phrasing traps is exactly what separates an A from an A star.
Act 5, the final system. The 3 rules for top marks. All right, we have successfully diagnosed the flaws. We've learned the vital vocabulary, we've operated the calculus engine forwards and backwards, and we've survived the pressure tests of real past papers. Now I want to crystallize absolutely everything we have done today into a concrete, repeatable system that you can take into the hall with you. Rule 1. Decode the command word. Before your pen even touches the paper to write a number, highlight the exact requirement. Are they asking for a time, a distance, or a velocity? Rule 2. Apply the engine. Scan the equation they gave you. If there is a t in the acceleration or a t in the velocity, you are dealing with variable acceleration, which means you must use calculus. Differentiate to move forward down the pipe, integrate to move backward. Rule 3. Execute the Peel framework. Point out your starting mathematical truth, like v equals 0. Evidence your calculus working step by step. Explain your algebraic factoring clearly, and link your final calculated number back to the exact command word you decoded in Rule 1. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So, let me leave you with this absolute, non-negotiable final rule burned right into your memory. Calculus must be used when acceleration is variable. If you remember absolutely nothing else from today's surgical session, remember that one fact. So, are you going to be the panicking data dumper, the careless sprinter, or the precise surgeon when you walk into that exam hall? Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.